It is 1 o'clock, October 18th. One of the concepts that we reviewed over, or the concepts that we've been going over recently, were introductions to trigonometry and leading into calculus. We've spoken about the structure of functions, the rules that go along with functions, and we reviewed the structure of a line function. Ms. Tihani, do you remember the line function equation?
Do you mean y equals b plus mx?
Exactly. Y equals b plus mx. Now, what this tells us in our function is that we have our function, which we represent as y, but soon I would like you to get comfortable with listing our function as f of the variable you're using, because later on in calculus, you will be using more complicated functions to represent functions in higher dimensions and using different variables, such as when you move on to functions in third dimension, you will be using a function of x, y, and z. And this will describe various models such as planes, spheres, cubes, just as simple examples. But listing function as f of x means that you are using a function in relation to x as the variable, as the variant. So the function changes dependent by the x. Does that make sense?
Could you go over that part, sir? I didn't quite get it.
Yes, that's fine. Let me try and rephrase it. So as we have it right now, we write our line equations by saying y equals b plus mx. The reason why we do it is that because in our graph, we have our y and we have our x, and we measure our function in terms of y. That's why the equation is written as y equals. As it is, this function represents y in relation to x. However, later on in calculus, when you are introduced to functions in 3 dimensions, such that you have x, y, and z, you will be using function in relation to either x or xy, xz, xyz. So merely stating that a function consists of dependent variables, x or y, etc., means that this function changes according to what you write in here. So because we wrote f of x, we say that this function changes according to x. Does that make more sense?
Yes, sir. Thank you.
Okay. Another thing to note is that if the function states merely that that it changes according to x, and you write b plus mx plus y, this means that because x is the only variable that the function changes according to, that means the b and the y must be constants. So that is what I'm trying to convey in a sense. but this isn't relevant as of right now. It is merely suggested. It is merely writing the function in such a way to get used to later concepts. What I want to focus on now is the structure of the line equation in relation to more complicated functions. Ms. Tihani, what does the b represent in the line function?
The B represents the intercept, the Y-intercept.
Very good. So the b represents y-intercept. Ms. Tihani, do you remember when we went over the position of functions?
Yes, sir.
So as we have it right now, the y-intercept represents where the line intercepts the y function at. But what did we realize when we changed what the y-intercept was? What is another concept that this b represents in terms of position of the function? Let me try again. What would happen if you increase the y-intercept by 1? So we'll say we have our function here. What happens if we add 1 to b?
The equation moves up.
Very
It
good.
moves.
Very good. The function moves up. So the idea is that the y-intercept is such that it represents the vertical position of the function. The way we write it in terms of position, we use y minus b plus m x minus 0. And that is what our function is. Oh, equals. Pardon. What this means is that the y-intercept represents the position of the y such that if you increase and decrease the y-intercept, you move the position of the graph up and down. So this concept will carry over to other complicated functions. So if you have y equals, let's say that we have a lot of complicated terms in here, but it is plus 2. What can you tell about this? Ms. Tiani? Are you there, Miss? Okay. What I'm trying to get across is that if you have a function y equals, so that inside of here, instead of mx, we have a far more complicated problem that if x equals 0, that this whole term equals 0 inside of it, that this will still be the y-intercept. And that you can still move this up and down by adding and subtracting it to move whatever this function will be up and down on the graph. Does that make sense? Please excuse me. There you
Sorry
go.
about that, sir. Is my Wi-Fi.
It's fine, Mrs. Tiani. So what I'm trying to convey is that if we consider our line function, so instead of mx, we represent a much more complicated function where at x equals 0, this term is 0. This plus 2 will still represent the y-intercept. Does that make sense?
Yes, sir.
Okay. So in the future, when we consider our functions, we can consider them y minus b equals some complicated function. And this will still apply to telling us the position of the function as to where its y-intercept is. This is not generally how people will write the equations, because oftentimes the way you can write certain equations such that you put the y-intercept on the other side conveys more information. But in the most technical sense, this is correct, because this describes the function in the correct form with its position. So, Ms. Tihani, do you recognize this? Sorry. Have you went over a function like this before?
No, I haven't.
Very good. Sorry, give me a second. So we have not gone over a function similar to this, but what we can say is that because of what we just went over, we can say that we can add a y-intercept here. So, and it won't change the nature of the function. All it would do is change the position of the function, which, as we went over before, only changes where it's positioned. Now, if we don't understand what the graph of this function will look like, what can we do, Mrs. Tiani? If we just say that this is our function. One thing we can do is that because the graph represents the relation between the functions, we can plug in values to the function and draw what the function should look like based on it. Does that make sense?
Yes, sir. I think so, but maybe when you elaborate more, I'll get it.
Very good. So one important concept to understand when we transition to more complicated functions like this is that when we think about it, if we went over a more simple function like a line where we said, let's say y equals 3 plus 2x, we would say we know that we start at 3 because when we plug in 0 for x, we have 3. And we can say that as we go over 1 on the x, we go up 2 on the y, because that is what our equation tells us. So this is a concept that we already inherently understand where if we don't memorize how the function looks like, we can simply do the math to list points on the graph, and from it, we can draw what the function should look like. Does that make sense?
Yes, sir.
Okay. Because I'm not sure if they went over this in geometry, but all forms of lines, shapes, and forms are simply constructed of dots. And it is the length of the length, width, and heights of the shapes that are constructed of a certain amount of points that form the shape. In this sense, what we can do is that we can say if we find the points on the graph, at least many points on the graph where the function is where the function tells us is by plugging in values for, let's say, the x, we say that the function has a point here, has a point here, has a point here, and has a point here. We can say that given what the shape looks like from the points, this is what the shape might be. Does that make a little bit more sense?
Yes, sir.
It's like how functions are sometimes formed in data tables, where you have an input and an output, where you list points on a graph, and this will tell you what the function is. We have at 0 is 10, at 1 is 20, at 2 is 30. We can say, okay, if these are the points on the graph, that means that this function might as well be y equals 10 plus 10x. And what happens is, as we take more and more points, it traces out what the function is. And that's what you will later understand to be a scatter plot, where you take as many data points as you can, you put it on the graph, and you begin to see what a curve or a line the function makes. Okay, does that make sense?
Yes, sir.
Okay, so let's take our equation y equals x squared. What we want to do is we want to start. How many points would you like to take, Mrs. Tiani?
3.
Tree? I think 3 would be a little low. I personally would recommend maybe 6, maybe 5 or 7. Because what you want to do is that you want to have 1 at the origin, so you know where the center is, the y-intercept. And then you want about 2 or 3 on each side of the x. Each side of the y-axis. You want some negative x values and some positive x values. That way, you make sure that you aren't just drawing lines, and you have a better understanding of the shape. But let's start with 3. So, Ms. Tiani, if we're using 3 values, then that means we can use -1, 0, and +1. Does that sound good?
Yes, sir.
Okay. Okay, Mrs. Tiani, what is y at x equals 0?
What was the question, sir?
That's fine. Here, let me draw a little chart. Drawing a chart would be excellent for understanding how more functions work. So on one side, you can put your X, on the other side, put your Y. So let's have a chart here, and let's say that these are our X values for this function Y equals X squared. This chart, in this chart, we will put what the X's and Y values are. So that means we get a set of coordinates, and we can put these coordinates on our graph. And at the points, it'll tell us what the function looks like. So let's try and fill out this graph. Does that make sense?
Yes, sir.
Okay. This is not the, I'm sorry. This is not the optimal way of, understanding how a function works. You'll have to understand that later on, but for now, it's a great way of doing it. So what is y when x equals 0 for function y equals x?
0.
Very good. So 1 point is at 0, 0. How about at x equals -1? What is
Positive 1.
Very good. And for when x is 1?
Positive 1 too.
Very good. So what this tells us is that we have a point here at the origin, a point here at -1, 1, and a point here at 1, 1. So if we use our points here, we can connect them with these little lines. And we can say this is what the function looks like for what points we have. Does that make sense?
Yes, sir.
Okay. So if we were to use just these 3 points, what would, if we use just these 3 points, what would we think that y would be at x equals 2?
It would be 4.
That would be if we use the equation, but I'm saying what does this little approximation tell us that the function would be at x equal 2 if we were to continue with this line?
Well, the y coordinate would increase.
Yes. So what I'm trying to convey is that from the little approximation of what we have the function that starts at 0, 0, and it goes to 1, 1. So if we were to continue using this approximation would tell us that this is a line that goes from 0, 0 to 1, 1, 2, 2. What I'm trying to say is that we want to take more data points to like greater understand how this function works. Does that make sense?
Yes, sir.
Okay. But as you said before, x equals 2, y equals 4. So what would y be at x equals -2?
It would be 4 too.
Very good. So Mrs. Tiani, can you tell why is it that both the negative x and the positive x each have positive values?
Because when a negative number is multiplied by another negative number, it equals to a positive one.
Very good. So what this means is that because it's squared, as you said, that means it'll be positive on both sides. What if I don't want any points, but what would happen if it was x to the power of 3? Would it be the same way?
The values would be different for sure. But yes, I would say it would be the same thing.
It would
No.
be this.
Yeah.
Continue. Oh, okay. So you were saying because it was to the power of 2, you multiplied two negatives by themselves, and that equals a positive number. So if you were to multiply a negative by itself 3 times, would that still make a positive number?
No, it will be negative.
Very good. So as we can tell, when x is to the power of 1, which is a line, we said that at of course, all of the x's will be positive for all of these. But for negative x to the power of 1, which is a line, will be negative. We're assuming that we have a positive slope. X to the power of 2 will be positive at the negative x-axis, and x to the power of 3 will be in the negative x-axis. How about x to the power of 4?
It would be -2.
It would be negative at the negative x.
Yes, sir.
Okay, so we would say it would be negative. Let's do the math as we've done for all of these. So let's say -1 to the power of 4. -1 times -1 times -1 times -1. What's -1 times -1?
I'm sorry, so what was the question? You
That's
broke
fine.
up a little bit.
So I was saying that if x to the power of 4 will also be negative in the negative x-axis, let's do the math quickly to show it. So I have -1 times -1 times -1 times -1. So let's start with right here, these two, -1 times -1.
+1.
Very good. And -1, -1 is +1. So now we were left with +1 times +1. So that means what, Miss Tiani?
That it'll be positive.
It'll be positive. Very good. Ms. Tihani, do you see a pattern?
Yes, I do.
Can you tell me?
Sure. After every number, it changes from the positive to the negative, and then positive to the negative again.
Very good. You're on the right track. Can we go further and say something even more definitive? How about this? We have 1, 2, 3, 4. We said that the 1 and 3 are negative and the 2 and 4 are positive. What do the 1 and 3 have in common that the 2 and 4 don't?
The 1 and 3 are odd numbers.
And the 2 and 4?
Even.
Very good. Thank you. So this is what we call odd and even functions. What this means is that the way they reflect in the y-axis is that when the function has an even exponent, then it's equally mirrored in the both the x and negative x side. If it's odd in the front, that means that the negative x is flipped over from the y to the negative y. All we really need to concern ourselves with at the moment would be x to the 3 and x to the power of 2 for right now. So let's go back to x to the 2. We said that 1, 1, 2, 2, no, 1, 1, 2, 4. What would it be at x equals 3 and negative 3?
You mean on the coordinates? On the
Yes, for x squared. So what would be y if y equals x squared and x was either 3 or negative 3?
it would be either 9 or negative 9.
Well, okay. 3 squared or negative 3 squared. Would either of these be negative 9?
Actually, no. Rethinking that, it won't be because negative and a negative will cancel.
Very good, because the function is even. So let's pretend up there is 9. So what these lines show us is that over time, the y consistently increases as the x's get further out, and they consistently and they increasingly increase over time. So they accelerate in the y direction. So what this means is that when we draw our y equals x squared, it will be a curve that looks like this. Does that make sense?
Yes, sir.
Okay. So this is the first curved function that you are introduced to. Now that we understand what it looks like, Mrs. Tihani, what would it be? What would it look like if it was, instead of y equals x squared, y equals 1 plus x squared? Are you there, Mrs. Tihani?
Yes, sir. I think it would be the same.
It would be the same. Would there be any difference? No?
There would be a change in the numbers.
Okay, so what would the change look like? That's what I'm asking.
Oh, so it'll be higher up because remember you're adding 1.
Very good. So what this means is that because we are adding 1, we are constructing our equation like this. So the y-intercept has increased because we moved the entire function up by 1. That is what we said as to how the position works. So the new function, as we just said, will be the same, just moved up 1, will now look like this. Does that make sense?
Yes, sir.
Very good. So instead of just saying y equals x squared, what would happen if we said y equals negative x squared? Do we know what will happen?
I'm thinking all of them will be positive.
Here, this is actually very important because now that you work with exponentials, it is very important to put your radius, just so you understand. So if the negative is on the outside, what do you think, Ms. Tiani?
If the negative is on the outside of the brackets, everything will be negative because the negative will apply to whatever is in the bracket, whether positive or not.
Very good. So what will our new function look like?
It will probably be a straight line or a curve only in the left-handed area where there's negative.
Okay. So let's try listing points again, just so we get it sure. How because the function is even, we know that both sides will look the same, the negative x and x, correct?
Yes, sir.
Okay, so that means we don't really have to worry about the x equals the negative x side. So let's just take 3 points on the positive x. What will y be at 0?
I'm sorry, what was the question, sir?
What would be y at x equals 0? We're doing the chart again.
It would be -0.
-0. I'll take it. There's not really anything wrong with writing it that way, even though it is still just 0. Okay, what about 1?
-1.
Very good. 2.
-4.
Very good. And 3.
-9.
Very good. So our function will look like this, and because it's even, the other side will look like this. Do you see a pattern?
Yes, I do.
Okay, so what happened when we made the function negative?
The curve moved to the bottom, which means that it lessened.
Okay, but what I'm trying to get at is before when we talked about the position of functions, one thing we reviewed is flipping functions. What we did is that we flipped the function over the x-axis by making the function negative. Because our original equation, y equals x squared, this was our function, we made that function negative when we set it like this. And when we take the function and we apply negative to it, this means that we flip the entire function over the x-axis. So it mirrors what it was like when it was on top, but now it's flipped over. Another way of looking at it is that now we made it -y equals x squared. So before, when we said what the x squared equals y to, now what we did is that we made all of the y's negative. So when we go back to our chart, for example, when we said we have our x and y, so at 0, it's 0, at 1, it's 1, at 2, it's 4, and at 3, it's 9. What we did is that when we made this whole function negative, it was the same as saying that we made the y negative, and it was still equal to the function. So now it's the y's that are now all negative. Does that make sense?
Yes, sir.
Very good. Now let's expand on this even further. Let's say we had y equals negative 1 plus x squared. Or no, that's not what I want. One minus x squared. There we go. What can we tell so far? Are you there, Ms. Tiani? So we have the function y equals 1 minus x squared. Hi, Ms. Tiani. So what we have so far is y equals 1 minus x squared. What we can say is that similarly to our line, we see that the y-intercept is independent of the function, at least in terms of the line as it is here. Similarly, we can see that we can bring over this number over to the y so that it is y minus 1 equals negative x squared. So this tells us that the y position is moved up 1. And the y-intercept is y equals 1. So we can say that our y-intercept must be here. In other words, whatever the function would have been without the 1 has been moved up 1. That is the purpose of this y-intercept. It tells us about the position. Now, if we say that the function is the same as the function without the y-intercept moved up 1 or moved up by the y-intercept, then that means that we can say we can take away the y. We can take away the 1, and we can just figure out what the rest of the function will look like and then move it up 1 later. So let's look at the function. If we didn't include the 1, we would see that it's y equals negative x squared. In other words, it's what we just did before. We said that before the y equals negative x squared will look like this. But now, because we introduced a new y-intercept and we made it y minus 1 equals the same function, that means we take this and we move it up 1. So the new function must look like this. Does that make sense, Ms. Tiani?
Yes, sir, although I missed out the first part of the explanation.
That's fine. So when we looked at this function, we said, okay, in relation to our line function, this is just the y-intercept. So we could take the y-intercept and move it over. And that means that when we take the y-intercept and we move it over, that means that if we just ignore it, that means it's this function just moved up 1 because that's what we said with position. So we recognize this because we did this just this last example, y equals negative x squared. We can draw y equals negative x squared as the function moving down again, and we just move it up. Now, there is another way of thinking about it in a more technical sense. This is where the charts are very useful because before we said that this is what describes y equals x squared. Let's say this is what our chart is. Y equals x squared is the same as y equals 1 minus x squared. These are both the same shape, what we call parabolas. I'll just write that. Each of these are a parabola. That is what this weird dome shape is. These are similar in the sense that if you take a chart and you say, okay, 0, 0, 1, 1, 2, 4, 3, 9, what difference, the difference between y equals x squared and y equals 1 minus x squared is that because the x is what the function is in relation to, if we set the x equal to y, because that's what the chart represents, what it tells us is that y equals x squared in relation to y equals 1 minus x squared, we set the x similar to y, we can see that it is simply the same y, but it is negative y minus 1. Okay, So the way that we would see it is that now all we have to do is that we take the original y values in the chart and we apply it to this, and we can see that the new y values, 0 becomes 0 minus 1, which is -1, times negative is 1, which we have here. 1 minus 1 times negative is now 0, which we have here. 2, no, not 2. 4 is 4 minus 1, which is 3, and -3. And 9 is now 9 minus 1, which is 8, and negative. So that means it is -8. Does that make sense?
Yes, sir.
Okay, so this is the technical sense of what is going on in this equation. So in this chart, when you think about it, you can solve for the x function. So you'd be solving for the x, or in this case, the x squared. And if you solve this for the x function, you can tell what the y will now look like in relation to the x. I want to go over one last idea. So let's now say x is equal to y squared. So instead of fx, we say fy. And this is the importance of stating it as function. So for fy, yikes. That means that since the function is of y, we are calculating x with respect to y. So that means it is with y that we will be counting x when y is equal to 1, 2, 3, 4, and so on. Does that make sense?
Yes, sir.
Okay. So because of the way we wrote it, we can simply take our graph and we can switch the variables. So this is x and this is y. This is essentially what we did. We switched around the x and the y. Earlier, we talked about this when we talked about flipping. This is called taking the inverse of the function. So we literally switched the x and the y by saying we inverted it across the line, inverted by flipping our function over y equals x. That's what we said we did. So Ms. Tihani, now that we have our x as the y and our y as the x, and we wrote it so that x is equal to y squared, what will this look like? Will it just look the same? Ms. Tihani, are you there?
Yes, sir, I'm here. I'm trying to work it out.
Okay. So one way we can think about it is that when we inverted the function, we just switched the x and the y. So we said that instead of y equals x squared, we just said that x equals y squared. And when what we just did is that we switched the y and the x on the graph. So if we switched everything, then that means it should look the same. The reason why is because if we draw on the graph x as x where the y is and y where the x is, then because x is the new y, and we flip the entire graph around, the function will look the same. Does that make sense?
Yes, sir.
Okay. So that means that this is what the function will look like on a normal uninverted graph. What we want to know is what it'll look like if we changed it so that we had y on the top and x on the bottom. Because we changed on the graph where the y is and the x is, that means we have to draw the function the way we did when we inverted the graph. So we drew a parabola where x was. So Mrs. Tihani, does that mean we also have to draw a parabola now where x is now?
Yes, sir.
Correct. So that's what I want to get across. The way you can think about it is because we switched around where the x and the y were, that means if originally the parabola went around where the y is and we switched where the y and the x was, that means we switched the parabola going around the y to the parabola going around the x. Does that make sense?
Yes, sir.
Good. So let's try and find out what this is then, this function. Ms. Tihani, do you think we can find out what the function of this is?
Yes, sir, we can.
Okay, how would you do it?
I would use the formula.
Which one?
The y equals the mx plus b one, and just replace the values.
Maybe, but as we have it here, that applies to a line. In standard, for the standard function, this describes the y-intercept and the function that goes along with it. So it's a little difficult to try and find out what it would be just from that alone. There is something, though, that can help us out. We said that when we inverted our equation from y equals x squared to x equals y squared, Ms. Tihani, now the graph is in terms of y, correct?
Yes, sir.
So that means that this function should be a function represented by y equals, correct?
Yes, sir.
Okay. We know that the original equation was x equals y squared. And now we want to find what y equals. Can you do that?
Yes, sir.
Okay, could you please do that for me? Do you have any questions or concerns so far?
Not really, sir.
Okay. How are you going about solving this?
I'm actually attempting to change the subject of the formula and see if I could get an answer.
Okay, very good. So just tell me if you have an answer. Ms. Tiani, do you have an idea yet? Ms. Tihani?
Yes, sir.
Okay, so what is your idea?
My idea isn't solid. I tried it, but it doesn't seem to be working out.
Okay. So one really good way of thinking about math is by sort of saying it to yourself what information we have, and it might become clearer. So what we had originally was that x was equal to y squared. That's what happened, we inverted it. And now we want to find out what this function would be normally. And the functions where the y is independent and the x is the variable we want to write it as y equals. So, Ms. Tihani, this is the real question. If x equals y squared, what does y equal? Does that give you an idea?
I kind of have the square root of x.
Very good. That's it. That's the function. That describes this. I want to do a chart again. So let's have our x and our y. What does our equation say that y is when x is 0?
It says that y is squared.
What?
So it will be 0.
Yes. Okay. How about at x equals 1?
It will be 1. Y.
Okay. So this is saying y is equal to x squared, or in other words, it is asking what squared equals x. So when we think about what things could be squared to equal x, we want to think. Is 1 all the things that 1 squared equals x?
Yes, sir. 1 squared will equal to x. If, of course, the 1 square represents the y.
Let me think about it in a better way. Okay. When we inverted our equation, we had it so that the x was on top, right?
Yes, sir.
So when we drew x equals y squared, x was on top, y was in the middle. We drew it like this, correct?
Yes, sir.
Because we said that this is basically a normal parabola. So at x equals 1, or in this case, when y equals 1, x equals 1, and when y equals -1, x equals 1. So we inverted it and we got this. So Ms. Tihani, isn't it true that, let's use another chart. Charts are a really good way of explaining things sometimes. Let's have 0, -1, and 1, x and y. Or in this case, y and x. Ms. Tihani, in this equation, x equals y squared, what is x if y is 0?
X will be 0 times 0, which will be 0.
Yes. What would x be in this equation if y was -1?
+1.
Very good. And what would x be in this equation when y is 1?
It would be +1 too.
Correct. So these two charts are the same equation, because that's what we said, that in terms of y is equal to square root of x. That's what we said, right?
Yes, sir.
So this chart is the same as this chart in a way. So this is saying, okay, now that we're saying that this is centered around y, we're saying that x is in relation, x is the variable. We're saying that what's true in this chart is true in this chart. So when we said that x is 0 when y is 0, we said that because x is 0 when y is 0, that means when no, I had it backwards. Because y is 0 when x is 0, that means when x is 0, y is 0. That makes sense?
Yes, sir.
Okay, so this means if we carry this over here, we say that because y is 1 when x is 1 and y is -1 when x is 1, that means when x is 1, y can be -1 or 1. Does that make sense?
Yes, sir.
So that means y is 1 and -1. This is because the square root of a number comes out to be two answers. It comes out to be the positive and negative of the square root. Does that make sense? I think we reviewed this before.
Yes, sir, we did.
Okay. This is just something you will need to remember when you do more complicated functions. This is why this is even. This is why a parabola is even, based on the notion that the square root of a number is two answers, or rather, when you flip it, you say that a positive 1 and a -1 squared both equal 1. That means that this equation, y equals the square root of x, will have two answers for an x value. And that's why we drew it this way. So if we apply this logic further, if we said x is 2, what would y then be?
It would be 4, sir.
You're on the right track, but you did it a little backwards. We're talking about y equals square root of x now. So if the x is 2, what would y be? Ms. Tiani?
Yes, sir. I don't know how I'm still getting 4 because when you transpose it, it'll be y squared. So.
But we're trying to find out what y is. So all we have to do is we have
So it'd be
y
square
equals.
root of 2.
Yes. And because it comes out to positive and negative of the square roots, it is negative square root of 2 and positive square root of 2. Does that make sense?
Yes, sir.
Okay. Ms. Tiani, do you remember the vertical line test?
The vertical line test.
Yes.
I'm not quite sure what it is. Maybe when we work it, I'll remember.
That's fine. So there is a rule with functions. So the rule of functions is that a function cannot have multiple y values. Cannot have multiple y values for at any one x. So this means that you can't have a function where x is two different values at the same time. So this is like saying if we had a chart and this chart said how many fingers I had at any given specific time, we can't say at one specific time that I have both 5 fingers and 6 fingers at the same time. That doesn't make sense, right?
No, sir.
Right. So this is saying that you can't have x, x cannot have multiple y values at any one point, because if you said that if you have a function, you said, so a function says some kind of y is equal to some kind of x. So if you said that x was equal to 1 and 2, or no, if you said that at x equals 1, y equals 1 and 2, you would say that because the y is equal to the x and the x is equal to y, if you say that y is equal to x and x is equal to y, that if y is 1 and 2 at a specific x, you would say that 1 is equal to x at that point. You'd say 1 is equal to x at that point, and x is equal to 2 at that one point. So what you are saying is that 1 is equal to 2, essentially. That's what the math process goes down to. You're effectively saying that then you have you have unequal numbers that are equal to each other. That's why this doesn't work. Does that make sense? This tells us why it doesn't work. You understand?
Yes, sir.
Okay. That's why the math doesn't really make sense. So the vertical line test says that if you draw a line vertical in a function and it hits multiple points, then it's not a function. Because that vertical line, if it touches two parts of the line or multiple parts of the line at one x value in this vertical line, that means it's not a function, because that means at one x point, there are multiple answers, and that doesn't make sense. That's what the vertical line test means. It's not a calculation as much as it is something that you can look at and it'll make sense. So that means that this isn't a function, technically. You can't have this be a function because it has multiple y values at any x. Does that make sense?
Yes, sir.
Okay. So this is where the important part comes in. We said when we solved our equation that y is equal to square root of x, which is equal to the positive and negative square root of x, correct?
Yes, sir.
So y is equal to the positive square root of x and the negative square root of x. So the way that we work around this is that we say that if y is equal to positive square root of x and it's equal to the negative square root of x, that means that we can write it as y equals square root of x and y equals negative square root of x. And because the y both use different functions, but these functions are technically the same, that means we can say that these are two separate functions that are still technically equal. So the way that we work around it is that we say that this is not one function, this is two functions, where you have one function on the top in the positive area and one on the lower in the negative area. And this is supported by what we talked about before with flipping, when we said that if we make the whole function negative as it is right here, then you flip it over the x-axis from the y to the other y, and that's what we can see here because it is vertically symmetrical. So this is two functions. What this means is that in math, when we go further, we have to make a certain clarification. When we write our functions this way, we have to either say, for this to be true, we have to say either x is equal to y squared, because that will cause us to get y is equal to positive negative, or we simply write y is equal to the square root. When we go further on, what you will see is that you will either see multiple functions contained within a variable that's set as to the power of 2 as we've written here, or you will see a certain equation written as something is equal to plus minus the square root. This is an important clarification because if you don't write it like this and you just write it as this, the assumption going forward is that you are simply saying the positive and only the positive. So if you write y is equal to the square root of x, it will be demonstrated as only this function. Does that make sense?
Yes, sir.
Okay, this is an important clarification. But simply put, this is how that looks. I think it would be good if we took a 5-minute break right now. And come back at about 31. Does that sound good?
Yes, sir.
Okay. Okay, you there?
Yes, sir.
Okay. So how are you understanding this so far?
Quite well. A few bumps, but
Anything else you'd like me to go over?
no.
Okay. So this is demonstrating the idea of how functions tend to work as you come in contact with more diverse functions. You can apply these same ideas to understand the nature of how these work and learn more about them. So that's an important distinction. So we put it right there. One other, I think one last kind of rule, not rule per se, an idea that we can address is the X-intercept. So the X-intercept, later on, we don't call them the X-intercepts, we call them zeros. The reason why we call them zeros is because later on, what will happen is that you will be given an equation like this, and you will have to draw what the equation is based off of this. You have to understand it visually in a sense. The zeros describe the x-intercept in this case. So later on, when you draw functions, you don't have to be exact. If anything, I would actively discourage you from trying to be exact because you will have to use equations with decimal points in them. And because of that, it's easier to just estimate because you can be terrible at drawing in math and do just fine, as long as you're technically correct. So when you are given an equation, there are really, I want to say 4 things that you want to know. One, you want to know the y-intercept. 2, you want to know the zeros. 3, you want to know the shape. And 4, you want to know the sign. There's like a 5 and a 6 and a 7 that I haven't gone over yet, but they're just more so details and things to remember. But as long as you get these ideas correct, then you'll have your perfect your correct drawing. So for these last 20 minutes, I think we can go over this. So, Mrs. Tihani, what can you see about this? What can you understand about it? Are you there?
I'm here, yes.
Okay.
I understand. I think I've seen that before.
But what does this give you any information from first glance?
Yeah, I could say that the one is the Y-intercept.
Very good. So if we think about our function in standard y equals b plus mx, this x describes the function in the x terms. So in this case, it would be these. In this case, the m would only describe a common multiple shared by these. So if this was 2x squared minus 2x, then you can bring out the 2, and that would be, in this case, the m. But in this case, just think of it as these are the x values of the function. So you're correct when you said this was essentially our y-intercept. So we can rewrite this as y minus 1 equals x squared minus 2x, just in terms of just in terms of technicality. Other people may prefer to just leave it as it is for a specific reason. But the way we have it right now, we can finish the equation with. But from here on out, I think it would be better if you just leave the y-intercept in like this. But because this is a really good function, a really popular and simple function, let's look at what we have here. We have y minus 1 equals x squared minus 2x. So we have our y-intercept, and we said that the y-intercept is at y equals 1, correct?
Yes, sir.
Okay. So sorry, I was just thinking for a second. As we have it here, I don't think we can find necessarily where the I'm sorry, I'm just thinking for a second. Okay. No, so here's what we want to do. Have you heard of factoring? Miss Tiani?
You mean factors?
Yeah, well, I guess not. Have you heard of FOIL?
No.
Okay, that might be a concept that we have to go over later. Means yeah, that'll have to be a concept that we go over later. But one thing that we can do is that we can say that the x-intercept is when the y is 0, correct?
Yes, sir.
Okay. So this means that the zeros will be the values that you plug into x so that y will be 0. So if we put our equation back, y minus 1 equals x squared minus 2x. Ms. Tihani, can we simplify this?
Yes, sir.
Okay, how could we simplify it?
We factorize, that is, we look at which factor is common in both sides, and we take it out and put the rest in brackets.
Okay, so we can do that with the right side of the function because we can say that there's x and x minus 2. Because we just took the x from x squared out and we took the x from 2x out. So there's this x on the front. What we know is that the x-intercept, the 0, describes when y equals 0, what the x is. So we want to rewrite our equation. So 0 is y. This is what our equation looks like. So 0 minus -1 is -1 equals x times x minus 2. So from here, what you would normally do is that you would try and factor this equation to find out what the x would be. Yeah, there's not really a good way of doing it without teaching you what factorization is or FOIL. But what I can say is that if we took this equation, we said that we're trying to solve for x. For this, what we want to do is that when we apply FOIL, we break this apart so that this is x minus 1 times x minus 1. This is equal to this. And what this tells us is that because we can see the -1 in the x minus 1, that the 0 will be at 1. And it's at here too, so it'll also be at 1. This is something I'll go over in next class. But does the idea make sense to you?
Yes, sir.
Okay. So this is the idea of what we will go over next time in class. But for all intents and purposes, let's say we figured out that the x's zeros were at 1. Right. Okay. So we know what the y-intercept is. It is at y is 1. And we know that the zeros is at x is equal to 1. So we can say that here and here will be on our graph. 3, we need to understand the shape. Yeah. For 3, we need to understand the shape. As it is right now, it would be difficult to understand what's happening. But if we break this down, we can see that it is x squared. So that means there is a parabola. And minus 2x means that you subtract from the parabola a line of negative, a line of 2x. So you have this parabola and you have this line, and you are subtracting from the parabola each of the points at the line. Does that make sense so far?
Yes, sir.
Okay. And what we know is that we have this parabola and we subtract from it this line, and we move what the total is up by 1 so that it will, the y-intercept is 1 and so forth. So I think the best way to figure out what the shape looks like is mainly by plugging in values. So let's try doing it with x is 1. What would be, no, that's the x-intercept, sorry. Let's try x at 2. Mrs. Tihani, what would be the value of the graph at x equals 2? So plug it into here and here. You know what? No, this is probably a terrible way to do it, actually. No, I don't want you to do that. Here's what I want to get across. The shape, we can tell what the shape is because in the front of the equation is x squared. That means it's a parabola. And there are not really too many instances where this is false. But the idea is that this is a parabola because the front is x to the power of 2. Does that make sense?
Yes, sir.
Okay. When we used FOIL, y equals x. No, we have it right here. When we used FOIL to find what the zeros were, to find x equals 1, this is what the equation is. So x squared minus 2x plus 1 is equal to x minus 1 times x minus 1. And any number times itself is that number squared. So that means that this is the same as saying x minus 1 squared. Y equals x minus 1 squared. And what the idea is that this is the same as y equals x squared. The only difference is that inside the x is minus 1. So Mrs. Tihani, do you remember position? What does it mean if we have x minus 1 on the inside of the x? What does that do to the position? I'll give you a hint. When we have its y minus b, that means you move it up by the b, and that's the y-axis. Ms. Tihani?
Yes, sir. I'm not quite sure.
Okay. So say you had a function, a line function, just say that it's y equals 1 plus x. What's the y-intercept, Ms. Tiani?
Sir, you broke up a little bit.
Okay. Ms. Tihani, let's say you have a line y equals 1 plus x. What is the y-intercept?
It's the 1.
Yes, because you write it as y minus 1 equals x. So in the y minus, because when you write it y minus 1, that means the position moves up by 1. So if subtracting 1 from the y makes it move up, what does subtracting 1 from x should do?
I'm thinking it would also make it move.
Close.
Move up.
You're close, because when you change the y, you're moving the position of the y up and down. When you change the position of the x, you're changing the position horizontally left and right. So if subtracting 1 from y makes it go up, then subtracting 1 from x should make it go to the right. That's what I'm trying to get across. So that's how we would find the answer, because we know that it has the y-intercept at y equals 1, x equals 1 for the 0, and the parabola, and we know it's a parabola because this is the same as this, but just with the x moving to the right one. That means we know that this is what the function looks like. Does that make sense?
Yes, sir.
Okay. I think I would prefer that you ignore this last example, because you would have to use concepts that you haven't learned yet, which I will go over next week. But this is an idea of what your future problems will be like in pre-calculus and calculus and so forth. Okay?
Okay, sir.
Okay. Do you have any last questions?
No.
Okay. Then that means we can end our session here. So, okay, that'll be